Welcome to our brief introduction to computer languages. So the title of the course is Introduction to Computer Languages. So what is a computer language? The simple answer is it's not a programming language, or we should say it's not just a programming language. Computer languages are tools that allow computer and information scientists to translate their ideas into something that can be represented on a computer. Now this does include programming languages like C++ or Java or Visual Basic, but it includes more than that. It includes markup languages like XML. It also includes design and specification languages like UML. Take a moment and see if you can think of any other markup languages or design and specification languages that you may have used in the past. Hint, hint, HTML is a markup language. Design and specification languages are something we're going to get into briefly in this course. You get into them more if you take higher level courses such as SP2018 or SP2018, but we're going to skim the surface a little bit here. These languages assist in translating concepts and ideas into a computerized format. Now for our purposes, again, we're going to be using UML. This will allow us to create things like use cases or sequence diagrams or activity diagrams or any number of different diagrams meant to visually represent a process or a system. It can also be used to represent how software is structured through the use of what's called class diagrams. That's what we'll get the most exposure to in this course. Markup languages you may have dealt with in the past if you've ever done HTML. These are used to indicate how a body of data, such as a document, is formatted when displayed on screen. That's really the purpose of HTML. Or it can be used to describe its logical structure. That's the purpose of XML, something we're going to look at in this course. Keep in mind that any notation for giving a computer an instruction or instructions is a programming language. Now, all of you have done programming in a previous course, whether that been IST 140 or CompSci 121 or what have you. You may have noticed that when you do programming, there's a certain algebraic quality to it. Well, the design and implementation of most programming languages is rooted in mathematical and computational theory. Specifically, most often, things like sets, functions, and what we call logic. Now it's important to remember that while the roots of a programming language are universal, how the language is implemented and the features it supports are almost always different. That's because languages are created for different purposes. They all are intended to give instructions to the computer. However, who creates them and why they were motivated to create them is what separates languages. Often languages are tailored to the preferences of the expected user community. There are some languages that are very well loved in the scientific community, and there are others very well loved in the business community. They serve different masters, but they have a lot in common. Here are some examples of programming languages. There are literally hundreds if not thousands of languages out there. These are just a few that you may have heard of and some that you may not have. Things like Java, JavaScript, Python, Ruby, Objective-C, C or C++, Visual Basic. Even SQL is a programming language. Remember, as we go through this course, where we're going to be doing a lot of programming, is that really programming is just math with logic. Now, engineering scholars will tell you that, well, there's engineering involved in here. Well, to some degree there is. As we get into larger projects, as you get into larger system creation, you pull in engineering principles. But fundamentally, programming is math and logic. Why is this? Why are programming languages based in the mathematical disciplines? Well, computer science grew out of math. And even today at some universities you'll see computer science as being offered by the math department. Why is this? Well, programming is used to solve problems via computation. And any problem that can be expressed symbolically or numerically is mathematical by definition. Ultimately, programming is just problem solving. We just use computation to do it. That said, programming languages are ultimately mathematical languages. Now here are some things you may have seen in IST 230. We're just going to review them briefly. First, an alphabet is a finite set of symbols, often represented by the Greek letter sigma. If we accept that as fact, a language is therefore a set of strings over the alphabet. In other words, combinations of the items in that alphabet. And here's an example. The set 0, 1 is an alphabet. If we string together a series of zeros and ones, and that means something to whoever created it, we can consider that a string over that alphabet, and it's the collection of those strings that form a language. Take a moment to review this before moving on. So what are formal languages? Well, programming languages are not only mathematical, but they're also formal. In other words, they're comprised of a set of statements that are deemed correct, quote unquote, by the language designer. The focus when it comes to languages is often on syntax, not meaning, at least when we talk about formal languages. Every language, whether it's a programming language or a spoken language like English or Spanish, has 4 facets. The first is syntax, or form. The second is semantics, or meaning. Grammar, which you can think of as formation rules. It's a little bit more complicated than that, but that's for our purposes here, that's sufficient. And pragmatics, which we'll talk about more here briefly. So what's syntax and grammar? These are often difficult concepts for people to wrap their mind around because they're kind of interrelated. The syntax of a programming language is defined by a formal language which describes what is correct or well formed. If you've done programming, you've encountered syntax errors when you've compiled your file. For example, in C++, if you forget a semicolon, you'll get an error, often more than one, which has its roots in a syntax error, i.e., forgetting that semicolon. The grammar of a programming language is a set of rules for forming strings from the alphabet and a set of rules for forming statements from strings. The grammar defines the syntax. Now take a moment to absorb that. The syntax of a programming language is precise with no ambiguities. It's important to remember that. This is not the vagueness of the English language, for example. It tends to be very precise because it has to be implemented on a mathematical device. And math is all about precision. Now, to give you an example in English, when we talk about grammar and things like that, you have these pieces, which are words. Maybe they're verbs, maybe they're adjectives, maybe they're nouns, whatever. The grammar discusses what's the proper way to put them together. And in the end, when we do things like a syntax check, what we're checking for is that we've implemented those rules correctly, or we're using those rules correctly. And that's the kind of thing that pops up in a compiler when you get a syntax error, or more appropriately, when you do a syntax check through compilation. So what does a compiler do? Well, for any language, a compiler or an interpreter must be able to determine the validity of the source code, in other words, the code you write. What it's checking for is whether or not that code is syntactically correct. Remember that it's not about meaning. It's not trying to determine if the code you wrote is correct in terms of solving the given problem. It's just checking that you form the words, phrases, and statements correctly. For example, in English, you could say something like, "The triangle screamed." Syntactically, that's correct, but it doesn't make much sense. But syntactically, it's correct. That's what a compiler is checking for. It's checking to make sure that you've applied the rules of the language correctly. It's not about the meaning. So what is semantics? Well, semantics is what we're talking about when we talk about meaning. They define the meaning of each construct. Now, for programming, what that means is it describes the effect of programs in that language, C++, Java, what have you, and the values that those programs will ultimately produce. In other words, what do these statements, or what do these constructs actually do? What do they mean? A programming language statement is evaluated for the effect it produces within a program. For example, an expression is a statement evaluated to obtain one or more values. Now, to give you an example from C++, x plus 3 is an expression. If x has a value, and being a variable it should, the value of the expression is a single value. Let's say x is 5. Well, x plus 3 means 5 plus 3, and the value that results from that expression is 8. A statement would be something like an assignment statement, where you would take that 8 and you would place it into a variable. So for example, y equals x plus 3 semicolon would be a statement in C++. Now, formal mathematical methods are often used to describe the semantics of a programming language, and there are formal documents out there you can find which describe the semantics of a language. Now, the reason for that is because natural language is fraught with ambiguity, and remember, we want this to be precise with no ambiguity. So what is this thing pragmatics? Well, this fourth aspect, pragmatics, means, is the language usable? There are languages out there which only the person who created it can understand or would want to actually use. It also includes the possible areas of application. Some languages are intended to be used on assembly line equipment, like for embedded systems. Some are intended to be used for scientific calculations. Some are intended to be used for web development. It all matter of where it's really intended for. The ease of use and implementation is also a part of pragmatics. Some languages are easier to implement and easier to use, generally speaking. And finally, the success of the language in fulfilling its stated goals. Languages are not just created normally for the heck of it. We want it to actually do something. For example, COBOL. Okay, they wanted to create a language that would be readable, that would be easily used by business professionals, and to a large extent they succeeded in that. So here are some key terms to remember as you go forward. Number one is the term computer language. Remember what it means to be a design and specification language, what it means to be a markup language, and what it means to be a programming language. Also know the terms mathematical language, formal language, syntax, grammar, semantics, and pragmatics. You may, hint hint, see these again, so be sure and review the notes that's provided to you. Okay, let's take a moment and watch a brief video where Steve Jobs discusses programming. And he has some interesting viewpoints on the subject which we can use to our advantage here.
If you're willing to sort of ask a lot of questions and think about things and work really hard, you can learn business pretty fast. It's not the hardest thing in the world.
It's not rocket science.
It's not rocket science, no.
Now, when you were first coming in contact with these computers, inventing them, and before that working on the HP9100, you know, we talk about writing programs.
Mm-hmm.
What sort of programs? What do people actually do with these things?
See, what we did with them, well, I'll give you a simple example. When we were designing our blue box, we wrote a lot of custom programs to help us design it. You know, and to do a lot of the dog work for us in terms of calculating master frequencies with subdivisors to get other frequencies and things like that. We used the computer quite a bit to calculate, you know, how much error we would get in the frequencies and how much could be tolerated. So we used them in our work, but much more importantly, it had nothing to do with using them for anything practical. It had to do with using them to be a mirror of your thought process, to actually learn how to think. In other words, I think the greatest value of learning I think everybody in this country should learn how to program a computer, should learn a computer language, because it teaches you how to think. It's like going to law school. I don't think anybody should be a lawyer, but I think going to law school would actually be useful because it teaches you how to think in a certain way, in the same way that computer programming teaches you in a slightly different way how to think. And so I view computer science as a liberal art. It should be something that everybody takes a year in their life. One of the courses they take is, learning how to program.
Yeah, but I learned APL, which, obviously is part of the reason why I'm going through life sideways.
Well, was it you look back and consider it an enriching experience that taught you to think in a different way, or not?
No, not that particularly.
Okay.
Not other languages, perhaps more so.
Yeah.
But I started with APL.
Uh-huh.
So this idea of programming as a mirror of your thought process helping you to learn how to think, is fundamentally why programming has become very popular, even at the K through 12 level, as a learning tool. Now, if we would have had regular class tonight, we would be doing these items in class. But go into Canvas, go to the Lesson 1 module, and complete the assignments that you find there. Be sure and check out the Canvas announcement as well. And I will see you in 2 weeks physically. But don't forget to do those assignments this week and be on the lookout for the online lecture for next week. Remember that next week is Martin Luther King holiday, so we don't have classes on the 15th either. However, there will be an online lecture or two that you'll want to check out. Have a great day.